Good afternoon, and thank you for joining us after a full lunch. And I hope you don't, doze off. But here we are. We are going to speak with Paul Garrison. He's a paleoecologist with Onterra, and he's speaking about history in the mucking.
So what I want to talk about for the next few minutes is actually give you kind of a history lesson. As all you know that, there's lots of sediment and muck at the bottom of the lake, and there's a lot of useful information in there. It doesn't just hold the water in the lake. It actually, if you know where to look, you can read the past history of the water quality and ecology of the lake like a book in what's been deposited in the sediments. So what I want to talk about for the next few minutes is, first we'll do the word of the day, which Sandy mentioned is paleoecology. And it's the paleo is means history. So it's the history of the ecology of the lake, paleoecology. We'll talk about why to take sediment cores, what kind of information you can get from that, how these cores are taken and how they're analyzed. And also what different land uses that have happened around the lake. As you all are aware, there's been a lot of changes in land use over the last 150 to 200 years. How have these impacted the lakes? And then what about climate change? We can actually use sediment cores to kind of see what's happened in the past and perhaps predict what we might see in the future in our lakes. So why take sediment cores? In most lakes, there's really a shortage of long-term data. If you're lucky, you might have data for 4 or 5 years, but really we want to go back to about 150 years, which is about how long it's been since European settlers have been in Wisconsin. So we take sediment cores to be able to go back in the history of what's changed in the lake. And as I mentioned, there's a wealth of information, which I'll share with you some of it, a small part of it that we see in our sediment cores, or in our lake sediments. So there's essentially two ways, or there's multiple ways to collect the sediment cores, but really all you need to do is you want to stick a plastic tube down into the, closer? Okay. Oh, there we go. So, so we just want to put a plastic tube down into the lake bottom and then extract some of the sediment. This is what as you can see, is called a gravity core. It looks like a bit like a guided missile, but there's actually a plastic tube within that core. Then you attach a cable to it and lower it to the bottom of the lake. And with this type of core, you're not limited by water depth. I mean, this is a type of core that they use in Lake Michigan and the Great Lakes. So as long as your core is, you can sample that water depth. We also use what's called a piston core. And in this case, this is actually a core that was taken on Isle Royal to look at changes in mercury deposition over time. This has a bigger core tube, so you end up with more material, but you're limited because you have aluminum pipes that are attached to it to about 40 to 50 feet of water depth. And then when we take these sediment cores, if you look on the right, what we're actually doing is taking different sections off from the sediment cores, and then we'll analyze the various sections throughout the core. So this is the number of lakes that when I was at DNR that we had sampled around the state. We're well over 200 lakes now. But the important thing is that, as most of you know, this area in the Southwest was not glaciated, so there are very few natural lakes. So most of the sediment coring we've done has been done in lakes that where there were glaciers. So there's two types of sediment cores that I've worked with. We have what we call a full core. This is sort of an example of what I showed from that core that we were taking on Isle Royal with the airplane. In this case, we take a core and we divide it all into sections throughout the whole core. And then we analyze anywhere from 15 to 20 of those sections spread through the core. We get a lot of information from a core like this, but of course it also costs a lot more to analyze a core like that. So what we do more frequently is we do a top bottom core. And so in this case, we would only analyze the top section, which would represent present time. And then we analyze near the bottom. And that we hope is prior to the arrival of European settlers. So this is when the lake was in its more or less natural state. Towards the end of the talk, I'll talk about cores that we've taken where we actually went all the way to the bottom of the lake, and then we dated that throughout the core. Typically, though, we only go back about 150 to 200 years, and the depth of that varies a lot from lake to lake. It may be anywhere, like in Big Green Lake, that was down about 12 centimeters, but if you go to a more eutrophic lake, it might be a meter. So the sedimentation rate varies a lot with the lake. If you do a full core, you, as I mentioned, you get a lot more information. This is also a good time to explain how most of these graphs that I'll put up are laid out. On the y-axis or on the left is the timeline. So it starts with the most recent time, in this case, 2000, back to older times. In this case, it's back to 1820. So it's as we would look at the sediment core, how we would lay it out. And then to the right, or the x-axis, then is the changes that we would see in whatever element we're looking at. So we'll see this type of display for a number of panels coming up. So how old is the sediment? The different layers that you're looking at. So the most commonly way we use is a method called looking for lead-210. This is a special isotope of lead. All over the world in the sediments, there's small amounts of the isotope of uranium-238. As that decays, it decays into radium-226. And as that decays, it becomes radon-222. And radon is a gas. It's also the radon that we worry about being in our basements and the gas and causing cancer. But for my purposes, it's very useful because radon goes into the atmosphere, has a very short half-life, and quickly breaks down into lead-210. And then as this lead-210, through precipitation and dry fall, falls into the lake. And since we know what the half-life is of lead, by analyzing the lead-210 in the core, then we can use a model to estimate when that section was deposited. Lead-210 has a half-life of a little over 22 years. So what that means is that if you start with 100 parts of lead-210 and in 22 years, you're down to 50 parts. In another 22 years, you'd be down to 25. So the bottom line is that essentially you can use this to date your sediment cores back to about 150 or 130 to 150 years, which is actually the time period we're generally most interested in. Now, you can't do this with a top bottom core, but you need to do this with a full core. What we can do with a top bottom core is we can analyze the bottom sample. And if we can't detect any lead-210, then we know that it was deposited at least 150 years. We can't tell you if it's 200 years or 300 years old, but we know it was before European settlers arrived. So as I mentioned, we use this lead-210 data to use a model to estimate then when the time was deposited. But models can be wrong. And so we look for other ways to verify the model. So one way we can do that is look for cesium-137. And cesium-137 is a byproduct of atmospheric nuclear testing. So the US first started doing nuclear testing with their nuclear bombs in 1954. So we know that when we start to see an increase in cesium, that time period is about 1954. But then when the Russians started doing their testing, their bombs were actually much dirtier than ours. And so they put a lot more cesium-137 into the atmosphere. But then in 1963, the atmospheric nuclear test ban treaty went into effect. And so then there was no more atmospheric testing of bombs. And so this peak then should correspond to 1963. And so that's how we check if the lead 210 modeling is correct. Now you don't see a peak at the top here, but if you were in Northern Europe, you would see a tremendous increase as a result of the Chernobyl nuclear power plant accident in 1986. But virtually none of that cesium made it over to the US, so we don't see a remnant of that. Another way that we can check our modeling results is in the southeastern part of the state, Wisconsin. In the 1960s, they used sodium arsenite as a form of macrophyte control. And so they kept records of how much arsenic they added to different lakes. So we can access those records. And so we know that in this lake in 1962 is when they added most of the arsenic. So this peak in arsenic then should correspond to the mid 1960s. And also on all lakes, we can look for stable lead. Now this is different than the lead 210. The stable lead was used as an additive in gasoline up until the mid 1970s. So this should also be another way to check the dating. So one of the fossils that is very useful in the sediments is actually this diatoms, which is a special type of algae. And if you saw the zooplankton talk this morning, they had some pretty pictures of zooplankton, but that's not what you actually see under a microscope. Well, it's the same thing with diatoms. This is not what it looks like under a microscope. It looks more like this. But the usefulness of diatoms is that they have shells made of silicon, which means they're preserved in the sediments for hundreds to up thousands to up to millions of years. And diatoms are very ubiquitous. They're found all over lakes, rivers, streams, and they also have a variety of sizes and environmental requirements. So some like to live growing attached to macrophytes. Some float around in the open water. Some like low phosphorus, some like high phosphorus. Some like low pH environment, some like higher pH environments. So by looking at the changes in the diatom community in the sediments, we can really get a good idea of how the lake's ecology has changed. So just to step aside for a minute, why do we care about phosphorus? You hear a lot of talk about how bad phosphorus is. Well, back in the 1960s, there was a big discussion whether phosphorus was causing algal growth, whether it was nitrogen, or maybe it was even carbon. So in Canada, in Western Ontario, they took a lake, they put a barrier across it, which you see in the middle, and then on both sides, they added carbon and they added nitrogen to the lake. But on this side, in the upper part only, they added phosphorus. And if you take a close look, this is a side on the lower left where they added phosphorus. And so clearly phosphorus is what was driving the algal growth. And so this was able to put this argument to rest. So that's why we concentrate so much on phosphorus. So what I want to go to next is talk about a few case studies where we've taken sediment cores. In most of these cases, we've taken a full core and looked at what the impact has been of different land uses. And the first one we'll talk about is agriculture. These lakes tend to be more in the southern and central part of the state. We'll talk about the impacts of early logging, especially in the central and northern part of the lake. As you know, there was a lot of logging activities, and of course, it really changes the landscape. So how much did that really impact our lakes? And then as you're all aware, we have lots of issues with shoreland development. There have been a lot of changes in types of homes and development around the lake. So what impact has that had? And lastly, we'll talk a little bit about climate change. So as you know, there's been a lot of changes in agricultural practices over the last 130 years. Initially, there was more subsistence farming. Tractors got came into play, the moldboard plow, bigger tractors. We farm more land now. And so what impact have we seen in lakes as a result of this? Well, the example we'll use is Green Lake. This is the largest natural or deepest natural lake in the state. And it has an area of over 7,000 acres, and the maximum depth is a little over 230 feet. This shows the watershed of Green Lake. Most of the browns and the greens are different agricultural land use. The purple up here, sort of to the right, is the city of Ripon. So some of the input from city of Ripon goes into Green Lake. But most of the large part of the watershed is agriculture. Let me go back. So one of the things we can look for in sediment cores is titanium. And the reason titanium is so useful is it's only found in clay particles. So we use titanium as a surrogate for soil erosion. So if titanium goes up, then we know the soil erosion is going up and more sediment has entered the lake. So what we see is that initially titanium goes up 1930s, 1940s, 1950s. And this was because following World War II, but also into the 1940s, tractors got to be more powerful and bigger. And so more farmland then was farmed than it had been before. And this introduced a lot more sediment into it. Then in the 1960s and into the 1970s, there was really a big push by the Soil Conservation Service, as well as local entities, to reduce soil erosion. And in the case of Green Lake, it actually was effective in reducing the amount of sediment that entered the lake. So the next panel we look at is uranium. And we don't really care about uranium per se, but a lot of commercial fertilizer has, as a contaminant, has uranium because of where the phosphate ore was mined. And so phosphorus changes a lot once it's in the sediments. So it's not as useful to look directly at phosphorus, but we use uranium as a way to look at how much commercial fertilizer was added to the lake. And as you can see, it really increased starting, in the 1950s and therefore. And the reason there was a big increase in the use of commercial fertilizers is that during World War II, there were lots of factories that were built to support the war effort and to produce ammunition. And as it turns out, it's not that much different process to produce fertilizer as it is to produce ammunition. So a lot of those factories then were converted into making synthetic fertilizers. So even though the soil erosion rates started going down in the 70s and 80s, 2000s, the use of fertilizer continued to go up. So even though there's less soil coming into the lake, there's more phosphorus coming in because of the fertilizer. And another thing we can use is magnesium. And we use magnesium. We're not concerned about the magnesium coming in from the watershed, but magnesium is one of the chemicals along with iron that when you lose oxygen in the bottom waters, it comes out of the lake sediments. So we look at changes in magnesium, and as it goes down, because it came out of the sediments, then we see less in the sediments. That's an indication of a loss of oxygen in the bottom waters. This would only work in stratified lakes. Lakes that do not stratify, this would not be useful. But what you can see in this case is that as use of commercial fertilizer increased, that's when we start to lose oxygen in the bottom water. It's an indication that algal growth has started to increase in the lake. And then, as I mentioned, diatoms are very useful for a number of features. And one of the things we can do with diatoms is that we've constructed models that if we know what the diatom community is, we can then estimate what the phosphorus concentration was at the water in the lake. And in this case, initially, as soil erosion rates started to go up, especially in the Western Basin, we start to see an increase in phosphorus. But even though soil erosion rates go down starting in the 60s and 70s, phosphorus levels continue to go up, and primarily that's because of the use of commercial fertilizers. So another lake that talk about with a lot of agriculture is Lake Ripley. This lake is just west of Madison, in the village of Cambridge. And in this case, we looked at this lake because this lake was one of the lakes that in the 1990s, the Department of Natural Resources, the Department of Ag had this program called Priority Lake Watersheds. And the idea was that lakes that were being impacted, not just necessarily by agriculture, but by urbanization and other things, was to find ways to reduce the amount of sediment and phosphorus coming into the lake. So initially, I took a sediment core in 1993 when this project started to look at it, what were the main causes of why this lake was degraded. But then we took another sediment core in around 2010 to see if the work that was done as part of the priority watershed really helped the lake. So going through this sediment core, initially in the 1900s, there was early farming, as well as this lake became very important with resorts. A lot of people from Milwaukee and Chicago came up and recreated at this lake. In the 1940s, there's a stream that enters this lake, and they channelized this stream or straightened it in many parts. And when they did that, it introduced a lot of sediment, but it was relatively short-lived. And then in 1990, as I mentioned, this lake became a priority watershed. They did some work in the watershed. Some of these wetlands, there's some wetlands that had been drained. We put these wetlands back into use, so they intercepted phosphorus. We did some stream bank erosion mitigation. We did some best management practices in the fields. And as you can see, the sedimentation rate or the infilling rate of the lake actually decreased. So there was some positive results from that work. Again, you can see the same results from the amount of soil coming into the lake. But phosphorus, and we see the same thing with the phosphorus. Phosphorus levels initially started to increase in the 1900s, 1920s, peaked around 1940 and stayed that way until the 1990s. So this priority watershed work was successful in reducing the sedimentation rate of the lake, as well as the phosphorus concentrations in the lake. So as I mentioned, and as you know, there was in the late 1800s and early 1900s in central and northern part of the state, there was a lot of logging that took place. But we don't actually see much of an impact from this logging on the lakes, which may seem a bit surprising, but if you think about it, even though the landscape changes a lot, you don't have big trees anymore, there's vegetation that quickly comes in and stabilizes the soil. So the impacts we see from this early logging are almost negligible on the lakes. So moving on to shoreland development, as most of you are aware, in the 1940s, the cottages were smaller. We didn't do as much lawn care, but then in more recent times, you get more impervious surfaces from larger structures. Quite often there's clearing all the way down to the lake. Another example is, this is Berry Lake. This is the property in 1940, the same property in the early 2000s. So you can see that the shoreline is much more exposed. So we want to look at what impact this shoreland development and changes in shoreland development is having on the lakes. So in the 1990s, as part of this type of work, John Panuska at the Department of Natural Resources developed a model where he looked at runoff of water, sediment, and phosphorus from lakes prior to cottage development, and then with early cottage development, and then in the 1990s. And as far as water runoff, he found that undeveloped in the cottages in the 1940s didn't really change it, but with larger homes, more impervious surfaces, we get a lot more runoff. We get a lot more sediment coming in. It increased some with early cottages, but it's really increased a lot with more shoreland development. And phosphorus levels running off should be a lot higher now than they were in the 1940s or in undeveloped. But and some others people also did some work at USGS and DNR where they directly measured how much phosphorus and water was coming from lawns and undeveloped areas and supported this in a number of ways. So this modeling looked like it, was indicating what was actually happening. Roughly around that same time, the Susan Borman, who did a PhD study on some lakes, seepage lakes in northwestern Wisconsin. And in the 1930s, as part of the Borman survey, there were some very accurate macrophyte surveys done in a number of lakes in northern Wisconsin. So she was able to get the survey data from 1930s, and then she replicated what they did in the 2000s as part of her PhD study. And what she found is that when they had the early cottages, many of the macrophyte communities looked like these short-growing needle-like plants called isoetids. But with the increase in shoreland development, we get a shift in habitat, a shift in macrophytes to ones that grow much higher, reach the surface. So there really is a big change in habitat in these nearshore areas, which he was able to document. And I took some sediment cores in the shallow areas and lakes she was working on. And this one on the left is marl down below. And then you can see the organic matter is built up on top. The same on the right. In this case, it was sand with some organic matter on top. So visually, you can see that there's been some big changes in these nearshore areas. And also around this time, when we were working on developing phosphorus standards for lakes, we did a number of top-bottom sediment cores at lakes all over the state to see if phosphorus levels now, how they compare to what they were historically. And in northern lakes, what we found, most of those have shoreland development, the phosphorus levels actually haven't increased over the last 100 years, even though the modeling results and direct evidence indicate we should have seen a lot more phosphorus coming into the lake. But we're not seeing that actually in the sediment cores. And what we think happened, this is just to remind you what the modeling showed, that we should be getting a lot more phosphorus coming in, is that, as you remember, what Susan Borman found was that in the 1930s, a lot of the macrophytes were very short growing. They weren't very high, but now a lot of these lakes have macrophytes that grow much higher. They're much denser macrophyte communities. And what we think is happening is all this macrophyte communities supports places for diatoms and other benthic algae to grow on. And so these diatoms are intercepting phosphorus that's coming in from the shoreline and taking it up and not allowing it to get to the open water of the lake. So this is why we're not seeing an increase in phosphorus out farther. Now that's not to say that there's not phosphorus coming in from the shoreline development. In fact, what I've seen in lakes in the southern part of the state with agriculture is that eventually you can overwhelm the buffering capacity from the algae growing on the macrophytes. And when you do that, that's when you start to see an increase in phosphorus in the open water, and you start to get algal blooms. So the biggest impact we've seen from shoreline development is not an increase in phosphorus in the lake, but a big change in habitat. So I want to wrap up with what we might see with climate change. I'll talk about two lakes that we took sediment cores, and in this case, we took cores all the way through the lake sediments. So we went back to about 13,000 years when the lakes were initially formed as the glaciers receded. We know from pollen studies that about 5,000 to 7,000 years ago, this region of the upper Midwest was warmer and apparently drier than it is now. And this is what's predicted to happen with climate change in the next 50 plus years. So we wanted to essentially use sediment cores to look at the history of the lake to try to forecast what we might see will happen in these lakes in the future. So the first lake we'll talk about is Max Lake. Max Lake is just west of Trout Lake. It's a small seepage lake. The size is around 12 acres. The maximum depth is about 15 feet. So we do a little bit of coring, different coring technique, but we take a sediment core. We can't take it all in one drive. So we have to do it in sections. So we take, in this case, the first drive, we took 1 meter of sediment. And then we had to carefully measure how long we had taken the first drive. We take another one, which in this case was 70 centimeters. So eventually we get to the bottom of the sediment, bottom of the lake, which is about 4.5 meters or roughly 15 feet. So in this lake, over the last 13,000 years, we've had a buildup of about 4.5 meters of sediment. So the way to look at this is that this one way on the left where it says 0, that's the top of the core, or where the sediments begin. And way on the bottom right where it says 450, that's the bottom of the sediments in the lake. So that represents sediments that were deposited when the lake first formed. So a couple things to notice visually is you see sort of this reddish brown color. This is mostly sort of clay with some little bit of sand mixed in, but it's mostly just clay. It's a little hard to see in this photos on the screen, but essentially these first two panels, it all looked the same. We didn't see much changes, but if you look at this third one, you can see a white line here, and you can see a white line here. And better resolution, you actually see more stratigraphy scattered throughout this, but you don't see that in either of these two on the left. So already you know that something's different was happening historically than we see happen in the lake now, just because of these different bands. So when you go back this far, you can't use lead-210 to date the sediment. So instead we used carbon-14, and carbon-14 can go back thousands of years. So what we find is that, well, first I wanted to highlight these two white strips and keep those in mind. So at the bottom of the core, it was deposited about 13,000 years ago as the glaciers receding. And so we have these different dates throughout the core. So one of the things that we found when we were doing acid rain research is that lakes in Wisconsin that have low pH, and I should mention that this lake naturally is acidic, has a natural pH of about 5.1. So what we found when we were doing acid rain research is that lakes that don't have streams coming in and don't get any groundwater or very little groundwater are naturally acidic. If you have a stream coming in, if you have very much groundwater coming in, there are some natural buffering chemicals, calcium and magnesium, in that water because of our geology. And then that keeps the pH of the lake higher. So instead of reconstructing the phosphorus in this lake, we reconstructed the pH. And this panel is different than I showed you before. The timeline is actually on the bottom. So we started at most recent time and then going back 13 to 14,000 years. And then on the y-axis is changes in pH. So as I just mentioned, if you have higher pH, then you have streams coming into the lake. If you have lower pH, then the streams are no longer coming into the lake. So what we see is that the pH has been declining over the last 13,000 years. So it appears and as I mentioned, 5,000 to 7,000 years ago, the climate was warmer and drier than it is now. So what we see happen is that from about 13,000 years ago to about 7,500 to 8,000 years ago, this was actually a drainage lake. Well, it's a seepage lake now. And then there's kind of a transition period in here. So when the climate was warmer and apparently drier, the lake levels apparently dropped in this lake, and it went from being a drainage lake to a seepage lake. Now, if you remember those two white bands, they're this point right here and this point right here. Looking at the diatoms in that, they were very much broken up. So those appear to have been two flood events. So clearly it wasn't a seepage lake then, or you wouldn't have had those flood events like that. So what we think actually happened in many of the lakes in northern Wisconsin is that this is Max Lake here. It's very small. This is part of Trout Lake over here. That all this hatched area was actually part of Trout Lake at one time. And then when the climate was warmer and apparently drier, lake levels dropped. Max Lake was separated from Trout Lake, and it's never been reconnected to Trout Lake. Much of this area that's hatched now is wetlands. So apparently prior to 8,000 years ago, those were all part of Trout Lake. So the last lake I want to talk about is Berry Lake. This is another seepage lake. It's a little bit larger than Max Lake, but also is relatively shallow. Has a maximum depth of 27 feet. This lake is just east of Shawano Lake. This lake undergoes a lot of water level fluctuations over time. This picture is taken in the early 1940s. You can see lake level is much lower. There's been other times when lake level is up to the edge of those trees. You can see all these docks are out of water right now. I should mention with Max Lake and also with this lake, this long core was done in conjunction with Dr. Samantha Kaplan at that time was at UW-Stevens Point. This is some work she's done. This is a relief map of this area. This is Berry Lake. You see these structures here. These are actually sand dunes that were formed as the glacier was receding, because in front of glaciers, quite often you have these intense katabatic winds, which blow the sand. Where Max Lake was situated, there apparently wasn't a lot of sand north of there, but between where Max Lake is and Berry Lake, there was a lot of sand, and these sand dunes formed, which you see here. And because of the way that the dunes are, we know which way the direction of wind was. So we took a sediment core from this lake. As you remember, Max Lake, to get to the bottom of the sediments, was 4.5 meters. Here, it was only a little over a meter, which is a bit of a surprise. We have the same red clay that we saw at the bottom of Max Lake, but here we have all this sand, which we didn't see in Max Lake. But then, as I mentioned previously, we got a lot of sand blowing in this area. So the first take is that this sediments in this lake are much shallower than they were in Max Lake. So we did carbon-14 dating again. And at the top of the red clay layer, it's almost 13,000 years. The top of the sand layer, it's a little over 11,000 years ago that was deposited. But then the big surprise is you go just a little bit up in the sediments, and it's only less than 3,000 years. So what happened in those thousands of years, what we think happened is that when the warm, dry period occurred in the 5,000 to 7,000 years ago, this lake dried up and a lot of the sediments went away. These are the rest of the carbon dating. So we've seen two results from apparently when the climate gets warmer and drier, and one is that lake levels drop, which is no surprise. Max Lake went from a drainage lake to a seepage lake, and Berry Lake dried up for a period of time. So in summary, paleoecology tells us what changes have happened in lakes and suggests what have been the major causes of the changes. Agriculture had a large impact on lakes, especially starting after the 1940s into the 1950s. Early logging really had very little impact. Shoreland development, while has increased nutrient delivery to the lakes, the macrophyte communities are able to intercept the phosphorus, but we do see a large habitat change as a result of shoreland development. And climate change will likely have important impacts on our lakes. So if you want to read more about this, I have 2 articles in earlier lake tide. You can go into the archives and from winter of 2007 and winter of 2008. And I'll be glad to take any questions if we have time. Just as an aside, this is Irving Lake at Vilas County, which had a lot of wild rice. And so we took a sediment core to reconstruct the history of wild rice in this lake. And in that case, we used rice pollen to do that. For Berry Lake. Yes. Yeah. Berry Lake Ripley. So Lake Ripley was part of a priority lake watershed. And so what they did in the watershed was wetlands that had been drained were reattached to the watershed. So they acted to intercept sediment and phosphorus. And then also best management practices like no-till plowing was enacted in the watersheds. And also they did some stream bank erosion to reduce the sediment.